Everyone, my name is Ashley, and I'll be walking you guys through question 3 from the CSM 61B Final Review Worksheet, MSTs. So for this question, we're given a graph, and it asks us, suppose we want to design a telephone network connecting all the cities labeled A to G in the neighborhood, and we'd like to do so with the least cost. So basically what this is telling us is that we want to create a minimum spanning tree within this graph that connects all the vertices, so we can have all the vertices connected to each other with the least possible cost. So part A of this question asks, given a graph with n vertices and m edges, how many edges form a minimum spanning tree? So let's go over what a minimum spanning tree is. So minimum spanning tree has three components: a minimum, so it's like least possible cost. It's spanning, which means it connects every single vertex. So in order to connect every single vertex, the minimum number of edges a graph must have is the number of vertices minus 1. Because if you have less than that, then it's impossible to connect all the vertices because there just simply aren't enough edges. And the next component is that it's a tree. So a tree also has a definition that it has exactly the vertices, number of vertices minus 1 edges throughout the graph, because it needs to connect every single vertice that's in the graph, or like in its tree. And it also has to have no cycles. And so if you have any more than a number of vertices minus 1 edges, then you have to create a cycle because it would be possible to get to the same vertex twice through 2 different paths. So as a result, we want the number of vertices minus 1, which is n minus 1 edges. And in the case above, that would be, since there are 7 edges, we would have 7 vertices, we will want to have 6 edges. And this is 6 edges specifically for the case above, because it's 7 minus 1. So let's go to part B of the question. So will the new graph contain any cycles? And then describe the structure. So as established before, the new graph will not contain any cycles because it is a tree, and trees cannot contain cycles. And describe the structure. As we established before, this new graph would be a spanning tree. So it will basically be connecting all vertices with the number of vertices minus 1 edges, and also it has a minimum possible weight. So it's also a minimum. So it's like it has the least total weight possible. So that should describe the structure of what the new graph should look like. And going into part C, it tells us there's one algorithm to find a minimum spanning tree called Kruskal's algorithm. So the way Kruskal's work is, at first you sort all the edges by increasing order of weight, and then you select the smallest edge and check if it forms a cycle within the spanning tree so far. If it doesn't form a cycle, you add it in. If it does, you ignore it and move on to the next smallest edge. And then so basically you just repeat the previous step until there's a number of vertices minus 1 edges in the spanning tree. Okay, so let's try running Kruskal's algorithm on the graph above. So I'm going to copy over all the vertices so we can see what our graph would look like. The original step 1 of Kruskal's algorithm is to sort all the edges beforehand. However, since we're doing it manually, it takes a long time and it's very tedious to sort beforehand. So I'm just going to sort as we go. So we want to find the lightest edge possible. So right now, the lightest edge is a tie between BC and EF. So in reality, it doesn't matter which one you pick because both would lead to a valid spanning tree. However, for the sake of consistency, I'm just going to choose in alphabetical order. So I'll be choosing BC first. So we check if adding BC to the new graph would create a cycle. Since there are no edges in the new graph, it would not create a cycle. So we can safely add BC, and we've added 1 edge to it. And just a reminder, since we have 7 vertices, we want to have 6 total edges. So that's the number of edges we want. I'll cross that out to show we already taken it. So the next smallest edge is EF because we already got rid of because BC and EF were tied and took BC. So we check if adding EF to this graph would create a cycle. It would not, so we can add it safely, and we add the second edge to our graph. And then, so we want to check for the next smallest edge. The next smallest edge in this case is of weight 2, so it's CD. So we check if adding CD to this graph would create a cycle or would not, so we can safely add it. So that's our next edge. And then we so that's all our edges of weight 2. So we want to look for edges of weight 3. There are no edges of weight 3, so let's move on to edges of weight 4. So edges of weight 4, we have A, B, and C, F. So once again, I'm going to use alphabetical order to choose A, B first. Adding A, B to this graph would not create a cycle, so I can safely add it here. And then we can check again with CF. Adding CF to the graph would not create a cycle. So we can also add it here as well. So we've added 5 edges, so we only need to add 1 more edge to reach 6 edges and connect everything. So let's move on to edges of weight 5. So we have 3 edges of weight 5, AD, CE, and DF. So our first edge is edge AD, and we want to check if adding it to the graph will create a cycle. We see that adding to the graph does create a cycle between A, B, C, D. So if we add it here, we'll have a cycle between these 4 vertices, which defeats the whole purpose of tree and makes it non-minimal, so we ignore it. So let's move on to CE. If we create a edge between CE and E, we would have a cycle from CE and F, and that would also defeat the purpose of a minimum spanning tree, so we ignore it. Then we want to add DF. Adding DF would create a cycle between C, D, and F, so we can add it as well. So let's move on to the next smallest weight, which is the edges of weight 6. So let's check adding AC to the graph. Adding AC would create a cycle between A, B, and C, so we don't want to add it. And we can check EG. Adding EG would not create a cycle in this graph, so we can safely add it. We have 6 edges, and we see all the vertices are connected. So this is how you run crossroads to create a minimum spanning tree. So let's go back to the questions. So the next question asks us, what is the difference between a minimum spanning tree and a shortest path tree? So a minimum spanning tree, basically, the purpose is to create like a tree or like a network that is a minimum possible network. So basically a tree with the least possible weight that connects every single vertex possible. Tree with least possible weights that connects every vertex possible. And however, a shortest path tree is slightly different. A shortest path tree is rooted at a certain vertex V. So how shortest path tree works is that the path from every other vertex to V would be the minimal path possible between those two. So it's not the optimal within everything, within the whole graph, but the optimal between V and every other point. So basically it chooses optimal least weight path between every single vertex and V source. So that's the definition. So the best way I like to think about it is like MSTs is finding the overall lightest, and shortest path is trying the individual like lightest. So the next question I asked, why would one choose Prim's algorithm over Kruskal's algorithm when Kruskal seems so much easier to compute? So the way to answer this question is we should look into the runtimes of each algorithm. So we see that Prim's algorithm has a runtime of O of E plus log V, while Kruskals has an runtime of O of E log V. So one is addition and one is multiplication. So the reason behind this is that Prim's algorithm continuously adds edges as we go. So basically it checks all the edges adjacent to the minimum spanning tree and then finds the minimum one out of those edges and adds it and repeats. While Kruskal sorts all the edges possible in the graph beforehand and then it continuously chooses lightest edge. So one instance where Prim's might be faster is when the number of edges is greater than the number of vertices. So this is because since there are more edges in the graph, that would Kruskals would have to look through every single edge before actually running an algorithm, or Prim's will run as it goes. So if there's a bunch of edges that don't like really matter in a minimum span tree, it will basically ignore it and be able to find a minimum span tree faster when there are long edges. So that's the case when we will run around Prim's, and this is when an edge, and an example of this would be a dense graph because that's the example of a graph with more edges than vertices. So let's move on to the final two parts of this question. Part 4, which asks, why does adding a constant value to each edge of the original tree not change the minimum spanning tree? So the reasoning behind this is that one thing you should notice that when you're running an MST algorithm is that it doesn't actually care about the weight of each edge specifically. It cares about the it only cares about the minimum weight of all the edges, or in which basically resolve a bunch of comparisons between different edges, seeing which one is smaller. So the thing is, if you add a constant value to each edge, then the inequality will still hold. Like if A is less than B and you add a constant value to both A and B, A will still be less than B, which doesn't defeat the minimum spanning tree algorithm at all. And to give a more concrete example of this, pretend we have two edges, one of weight 3 and one of weight 5. Edge A has a which has a weight of 3 is less than edge B, which has a weight of 5. So it will choose 3. So pretend we add a constant value of 2 to both sides. So we would have 3 plus 2 and 5 plus 2. And in this case, we have two new numbers, 5 and 7. 5 is still less than 7, so we'll still choose edge A. So no matter what value you choose, the inequality will still stay the same, and therefore the minimum span tree will also not change. So just to write this down, I'll say adding constant value does not change inequality. So the last part of this question asks, do Prim's algorithm and Kruskal's algorithm work if there's if there are negative edges? So the short answer to this is yes. And one way you can easily prove this is if you let's pretend you can't actually it doesn't actually work for negative edges. But then since we established that adding constant value doesn't to each edge in the original tree does not change the original minimum spanning tree, we can easily just add a positive number constant value to each edge and make it positive numbers, and therefore just making it a normal minimum spanning tree. Like for example, if we have a minimum span tree or a graph of weights -5, -2, 1, we can add 5 to all values, and that would create a new graph with all non-negative values. So it'll be 0, 3, 6. And even if you don't transpose the numbers that way, you can still run it normally. Because like I said before, the MST algorithms only care about the comparisons or relationship between edge weights rather than the edge weights themselves. Therefore, 0 is still less than 3, so which is what we'd be checking over here. But over here, we just check if -5 is less than -2. And in both cases, it's the same inequality both times, and it'll always hold. So therefore, we can run Prim's algorithm and Krusk's algorithm on negative edge weights. So hopefully that helped you understand min spanning tree and Krusk's algorithm better. Thank you guys for watching, and good luck on the final.